G'day chemists. Today we are going to talk about emission spectra. It's this wonderful idea discovered just over 100 years ago about how when we get electrons excited, when they've sort of calmed down a little bit, how they release a light, and that bit of light they release can tell us a lot about it. Like, for example, what the atomic structure is a little bit, which atom we're looking at, and so forth. So let's dive in. So first off, electron energy absorption. So first off, electrons, they travel really fast, right? Like they just sort of hoon around the nucleus in principal quantum energy levels. That's what in earlier years we've called shells. And each electron's kind of got its own shell that it lives in. Well, it shares it, depending on what you're talking about. And that shell that it lives in primarily, or where it's like located before it gets excited, is called its ground state. And we see they're numbered N1, N2, N3, and then N4, 5, 6, and so on. And those are the principal quantum energy levels, which again, in your junior years, you probably called electron shells. So if your electron absorbs enough energy, but specific amounts, it's going to jump to a new discrete energy level. So that means it doesn't exist. It doesn't travel halfway between energy levels. It goes from one to the next, and it doesn't exist in between. It just goes boom, boom. It makes that jump. Typically, it's like electricity, heat, or light that we're making that happen with. So we call this an excited state. So when it's not in its ground state, so if we've got an electron from N1 and we heat it up, and it moves up to N2, that's in an excited state. But it might also skip that. It might absorb just the right amount of energy to go to N3, N4, and N5, even N infinity, which means something particular, but don't worry about that, that's for another lesson. But then we have this process of photon emission. So as it jumps up, it's unstable and it doesn't stay there. And eventually it loses that energy and it jumps back down. And we say jumps, by the way, it jumps up or down. So we say jumps because it doesn't travel between. It goes from bang, bang. Remember, it's like it does not exist in between those states. It just sort of pops up here, then it pops up down there. So as it jumps to its ground state, because of the law of conservation, that means energy's being lost. So it has to actually lose some energy. It can't just move from one to the other. It releases that energy as a photon, that has a specific energy / wavelength. And those are numbers which are not the same, but very much related. So this is called a photon emission, yeah? And it produces light at specific wavelengths that are characteristic of that element. So we can actually use it to tell if it was a hydrogen, helium, and so on all the way up. Every element has its own specific set of lights. So this energy will have the same frequency as the absorbed if it goes the other way. So if we have a cold gas and we shine light through it, it will absorb the light of the same frequencies, but in the other way, right? So instead of getting a full rainbow on the other side, we get the full rainbow minus the specific wavelengths that it absorbs or as it would emit. And we'll see that in a second. So this is what it looks like, right? We have photon in this case is the energy, so light hits it, it's the right wavelength, it goes up to an excited state, but then it drops back down, and as it does, it re-emits that photon or the heat energy, but turns it into a photon, whatever it is that goes out. And that photon is very much a very specific wavelength. And we see that here, right? We'll do calculations at a different point. The electrons we're talking about are always like the valence electrons, like the most outer shell electron, and is the most it's the first ionized electron of that crew as well. So this gives us an emission spectra, which is this bad boy here in the middle. So here, if we'd have continuous light, right? So this continuous white light gives us this continuous emission spectra. Continuous spectra, not an emission spectra. But when we have a specific electron, right, like it jumps up, and then it jumps back down and releases very specific photons, not a continuous one. That's when we get these lines. And those are the only ones that it released. And that's interesting in itself. But, so we call that the emission or line spectrum. And it means that there are like discrete quantum of energy levels. And it also implies that, because this is all one electron, that different atoms, but the same electron, that there are multiple energy levels it can jump to, okay, because there are multiple lines, but, and this is the fun part, it means that it can only exist in certain energy levels, which means it can't exist between shells, right? It can only exist in its specific shells and subshells. So that's how we know electrons travel around the outside in certain orbitals and groups, and it can only be in those orbitals. It can't be in between. All right. So, and again, we talked about before, if we pass energy through a gaseous, we call it cold gas, but it just means like not to the point where it's electrons are excited. Through a gas, it will absorb in the opposite, like it'll produce the opposite spectrum here. All right, and that brings us to another idea, the limit of convergence. This is a fun one, right? So you'll notice here our emission spectra, this is still hydrogen, has been flipped around. So we have the blue on this side, and that's because the blue is the shortest wavelength, but the highest energy or frequency. Okay, so as we get closer to the higher energy end, we end up with like more and more lines, and that's called convergence. And then towards the blue end, again, there's more lines than the red ones. As they come together to like the maximum, and it's different for each atom, we call that the limit of convergence. And at the limit of convergence, that corresponds with the amount of energy. So when we hit that point there, like that's the end, or actually that's the end there where they've all come together, where we hit where they've all come together, like beyond that point, any electron is then removed. So that energy level right there, beyond that, and that's why there's like a whole spectrum beyond that, the electron, it doesn't go to like N1, 2, 3, 4, 5, 6. It goes to N infinity, and it is yeeted off the atom altogether. And that's called first ionization. So that's the first ionization energy, is at the convergence limit right there. These were first discovered by a Swiss school teacher. He's a school teacher, so obviously we quite like him, named Johannes Balmer. And he discovered it in the visible spectrum. And this group here, when we see that, is known as the Balmer group or Balmer family. And if it's in the visible spectrum, what that actually means is that as it drops down, it's going to energy level 2. And there's different ones in like the UV, IR spectrum for different shells, but that's just where the visible one happens to be. I hope that made a lot of sense. If you have any questions, put them in the comments below, and we'll get back to you as soon as we can. Thank you for watching, and we'll catch you next time. Bye now.